Yes, sir. Well, thank you all for sticking around. I'm going to share with you today some of the research we've been doing at RPI over the past year or so. I'm trying to develop a new tool for understanding the provenance of sediments using the trace element content of quartz. So the primary objectives of the study are to first demonstrate that the trace element content of quartz, particularly in this case we're going to focus on titanium and aluminum, reflects their chemical environment during crystallization. Oh, thanks. And second, we're going to try to use the trace element composition of the quartz ex situ in a modern drainage basin to understand the sources of sediments in the basin. So why look at quartz first? As we all know, it's a common mineral on the Earth's surface. So quartz-based provenance can be used in a wide range of geologic settings across the globe. Secondly, quartz crystallizes in a wide range of geologic conditions, so from plutonic to volcanic, in high-temperature veins and pegmatites to metamorphic systems and low-temperature geodes. So when you think about traditional provenance indicators like zircon, which crystallize in plutonic and volcanic systems and high-grade metamorphic systems, the fact that quartz crystallizes at low temperatures allows us additionally to sample a wider range of geology with the quartz. Thirdly, there's a limited trace element solubility in quartz, which has been experimentally constrained in some cases. So again, we're going to focus on aluminum and titanium in this study. And they both substitute onto the tetrahedral silicon site in the quartz. There are also important interstitial substitutions for lithium and hydrogen. And when we think about the substitution mechanisms for titanium and aluminum, titanium substitutes in a one-to-one for silicon on the tetrahedral site, whereas aluminum, because of a charge deficit, substitutes with monovalent lithium or hydrogen, which has been demonstrated by Nick Tailby and others in a wide range of geologic systems. And finally, as alluded to in the previous slide, we have some understanding of the trace element composition of quartz and the dependence of the solubility on thermodynamic principles. So in this figure, I'm just showing isobars of titanium versus temperature. And so in terms of titanium, we understand that its incorporation into quartz is a function of temperature, pressure, and the activity of titanium. And with aluminum, it's also a function of temperature and pressure, the activity of aluminum in the system, as well as the pH and the activity of lithium due to that charge balancing coupled substitution. So for the rest of the talk, I'm going to be focusing on the Bega River catchment. And since this is a preliminary study, doing something that's not really been done before, we have to kind of step back and try to answer a couple of basic questions about quartz. So first, does the chemistry of quartz in a drainage basin reflect the chemistry of the bedrock quartz? And second, does the quartz retain its primary chemical signature through weathering and deposition? So is this even a viable mechanism in the first place to understand sediment provenance? So we're focusing on the Bega River catchment and the Lachlan Fold Belt. So many of you probably know the Lachlan Fold Belt as the prototypic I, S, and A type granitoid complex described by Chappell and White. And our study area is down here in this little red rectangle. So if we zoom in, the Bega River catchment is outlined here in the dark black polygon. And the first thing you notice is that the majority of the Bega batholith, the Bega catchment, is taken up by the Bega batholith. And these are parametaluminous I-type granitoids. In particular, the majority of the batholith, the majority of the catchment is occupied by the Bemboka granodiorite. There are also some sedimentary units in the northern portion of the catchment that predate the crystallization of the granites. And there are some paraluminous granitoids to the west of the basin. And so if we think about the bulk rock chemistry of granitoids, paraluminous granites typically have elevated aluminum content, and we would expect that to be reflected in elevated aluminum activity, which would also therefore be reflected in higher aluminum concentration in the quartz. So the black circles are our bedrock sample locations, and we sampled the sediment near the mouth of the river to try to maximize the drainage basin sampled. And just one more thing to note, there are also a small volume of paralkaline A-type granitoids in the catchment. So briefly, we did all of our analyses on the Bruker 820 MS, LAICP MS at RPI using an 80 micron spot size, the laser frequency of 6 hertz, a laser energy of 8 joules per centimeter squared, and a 40-second acquisition time. So with the time-resolved ICP-MS spectra, we were able to filter out any possible mineral or metal inclusions to make sure that our analyses are reflecting lattice trace element compositions. So now I'm just going to show some data from the catchment, from the granites within and from outside the catchment, as well as some data from veins from Allen and Yardley. So in aluminum space, you can see right off the bat that peralkaline and peridotmetaluminous granitoids have very similar histograms in aluminum space. And as would be expected with the periluminous system, given the elevated aluminum activity, you also see an increase in aluminum concentration in the quartz from the periluminous granitoids. Veins show a wide distribution of aluminum content, which we believe to be a function of the solubility dependence on pH. So if we plot the, wrong way. So if we plot the composition of the sand shown here, again, the majority of the bedrock in the Bega River catchment is I-type granitoids, and that appears to be reflected in the histogram for the sand, where the histogram lines up very well with the peridotmetaluminous I-types and the peralkaline A-types. You also see a spread toward elevated aluminum, which could be from S or S-type granitoids or veins, but purely in aluminum space, it's a little bit difficult to deconvolve those two. So if we look at titanium, the first thing you'll notice is that the vein concentration of titanium is very low. So solubility of titanium is very low at these low temperatures of vein formation. Another thing you'll notice is the peak. The main peak for the sand aligns with the main peak for the periluminous granitoids, as well as a smaller peak for the peridotmetaluminous I-type granitoids. So in titanium space, it's not necessarily easy to discern the difference between peridotmetaluminous I-type sources and periluminous sources for titanium. Although I will note that the Bemboka granodiorite, the most prominent plutonic rock in the region, is this little hump in titanium right here. So next, I'm just going to convolve aluminum and titanium and see if we can pick out some differences in the granitoid quartz. So what I have drawn on here are a couple of dash lines delineating the different possible sources of quartz in the basin. So first, I've drawn a dash line between magmatic and non-magmatic sources. These are dash lines intentionally. These are permeable barriers. With the intrinsic heterogeneity of geologic systems means that you are going to get some vein quartz having elevated titanium, and you are going to have swapping of quartz between the different granitic fields. But in general, these dash lines hold for this system and others. So the 20 ppm line, if you think about it in terms of the titanium and quartz calibration, using a 5.5 kilobar estimate from mafic enclaves in the Lachlan Fold Belt and a near solidus granodiorite crystallization at 620 degrees, you get a minimum activity for titanium of 0.28, which is broadly consistent with the results observed from Nick Tailby and others on granitoids. And then just briefly, I'm going to talk about this little slope right here. You can notice general trends in increasing titanium and aluminum space for all three of the granitoid types. We believe that's just simply a function of the increased solubility with temperature. So we've drawn a dash line here basically just on visual inspection to maximize the delineation between the granitoids, but I think you could argue for a parallel slope to this lower titanium value based on the limited number of samples up at the high titanium range. Okay, so next I'm going to plot the composition of the sand in the basin and see what we get. So as expected, based on the bedrock composition, the majority of quartz in the sand at the mouth of the river lies within the peridotmetaluminous and peralkaline field. So as noted earlier, the peralkaline A-type granitoids and the peridotmetaluminous I-types are difficult to distinguish in terms of their chemistry, but in terms of the relative volumes within the basin, we're going to assume that most of this stuff comes from the peridotmetaluminous granitoids. And notably, there's also quite a significant contribution to the sediment in the periluminous field and a small contribution from veins. This is not terribly surprising given the fact that the sediment was sampled near the mouth of the river, so there could have been open system mixing with sediments from the Pacific. as well as contributions from the sedimentary rocks in the catchment, which we do not sample. So now I'm just going to briefly talk about some of the future applications of titanium and aluminum and quartz as a tool for provenance. So this was, again, a preliminary study based on a confined basin with well-understood bedrock lithology. But I just wanted to point out that this could be, these types of applications could be used globally where quartz is present. So we're working on currently creating 2D probability density functions of the quartz populations that Nick Tailby has been analyzing from a wide variety of granitic sources to basically allow other people to estimate the most likely source composition of quartz in their sediment samples. Also, notably remiss in our sampling is metamorphic systems. So we would expect most, well, we've seen in a couple instances, most quartz plotting down here, as would be expected by the titanium and quartz thermobarometry, but they could also, in higher grade systems, come down into this lower granitic source. And again, I just wanted to emphasize that this is not necessarily just useful for modern sediments. This could be used anywhere where there are anywhere where quartz is present and it has not been recrystallized from dynamic recrystallization or dissolution precipitation. So just to conclude, recapitulate those questions. Does the chemistry of the quartz grains reflect the chemistry of the bedrock? Yes, at least in the Bega River catchment, we see evidence that most of the sediment load in the basin reflects the bedrock lithology, and there is some source contribution from either sediments in the system or open system behavior near the mouth of the river. And does quartz retain its primary chemical signature through weathering and deposition? Yes, at least for titanium and aluminum in this case. But again, dynamic recrystallization or dissolution reprecipitation of quartz post-deposition will erase the primary chemical signatures. And with that, thank you.
We have time for questions. Yeah.
How diagnostic would individual analysts be to this? So, for example, if you had two paraluminous analysts in your catchment,
Yeah. It really depends, as you might expect, on the plutons. So, for example, this lower titanium and aluminum population of quartz right here is the Bemboka granodiorite within the basin, but other granodiorites of similar composition plot up here at a higher titanium field. So it really depends on the composition. You said paraluminous. Most paraluminous granitoids lie really close down here. So if you look at the 2D PDF, I mean, basically they all plot right down here, whereas you get some scatter up here, which you might expect given the nature of paraluminous granitoids. Well, I mean that's definitely one of the benefits of quartz-based analyses is that you could just take a thimbleful of sand from your sediment, mount it in epoxy, and put it on a laser ablation, and in a day you could have 300 plus analyses with very little filtering. So in that sense, it's a very easy technique. Of course, you're not getting temporal data like you do for detrital zircons, but in terms of the volume of sediment and the ease of doing the analyses, it's much better.